Hello, today we're going to master three-dimensional geometry. By the end of this session, you will be able to apply Pythagoras' theorem and trigonometry to solve complex 3D problems and calculate the angle between a line and a plane, just like you would see in an IGCSE exam. Let's look at our learning objectives for this lesson. First, apply Pythagoras in 3D. Second, use SOHCAHTOA in 3D shapes. And third, identify and calculate the angle between a line and a plane. When we move from 2 dimensions to 3 dimensions, the math stays the same, but the challenge is seeing the right-angled triangles hidden inside the shapes. We will start with a classic cuboid problem to warm up. Let's dive into our first example. Imagine a cuboid where the base is a rectangle. We want to find the length of the internal diagonal, which is the line connecting corner A to the opposite top corner G. To find the length AG, we first need to find the diagonal across the floor of the cuboid, which is the line AC. Notice that triangle ABC is a right-angled triangle on the base. We can use Pythagoras' theorem, AC squared equals AB squared plus BC squared. AC2 squared equals 8 squared plus 6 squared. 64 plus 36 is 100. So AC is the square root of 100, which is 10 centimeters. Now that we know AC is 10 centimeters, look at the vertical triangle ACG. Because the edge CG is vertical and AC is on the horizontal base, the angle ACG is 90 degrees. We apply Pythagoras again to find AG. AG squared equals 10 squared plus 5 squared, 100 plus 25, is 125, so AG is the square root of 125. Using a calculator, the square root of 125 is approximately 11.18 centimeters. This two-step process is the bread and butter of 3D Pythagoras questions. Now, let's tackle a concept that often appears in the harder part of IGCSE papers, calculating the angle between a line and a plane. Think of the plane as the floor and the line as a slanted pole. The angle we want is the one between the pole and its shadow on the floor. If you imagine a light directly above the cuboid, the line AC is the projection of AG onto the base. The angle we are looking for is angle GAC. We'll mark this angle with the Greek letter theta. We already know the lengths from our previous step. The height CG is 5 centimeters, and the base diagonal ACG is 10 centimeters. We have a right-angled triangle ACG. To find the angle, we use the inverse tangent function. Using your calculator, this gives us an angle of approximately 26.6 degrees. Remember the key rule: to find the angle between a line and a plane, drop a perpendicular line from the end of the line to the plane to create a right-angled triangle. Let's try a more challenging shape often found in exams: a square-based pyramid. In this problem, the square base has sides of 10 centimeters and the slanted edges, like VA, are 12 centimeters long. Our objective is to find the vertical height of the pyramid, VO. First, we'll draw a dashed line from V to the center O and another line from O to corner A. First, we need the distance from the center O to a corner A. Since O is the midpoint of the diagonal AC, we first find AC using the base triangle ABC. We use Pythagoras on the base. A c squared equals 10 squared plus 10 squared. This gives us AC squared as 200, so AC is the square root of 200, which is approximately 14.14 centimeters. Since OA is half of the diagonal AC, OA is 7.07 centimeters. Now, look at the internal triangle VOA. This is a right-angled triangle because VO is the vertical height. We use Pythagoras' theorem again, but this time we are solving for a shorter side, VO. Plugging in our values, VO squared plus 7.07 squared equals 12 squared. This simplifies to VO squared plus 50 equals 144. So, VO squared is 94. Finally, VO is the square root of 94, which is approximately 9.70 centimeters. The height of the pyramid is 9.70 centimeters. Notice how we always look for that flat triangle sitting inside the 3D space. For our final example, let's find the angle between a sloping face and the base of this same pyramid. This is a common grade 9 or A-star IGCSE question. The angle between the face VAB and the base is not the same as the angle of the slanted edge. We need to use the line of greatest slope, which goes from the vertex V to the midpoint of an edge, M. The triangle we need to look at is VOM. Because O is the center and M is the midpoint of the side, the distance OM is simply half the width of the square. We want to find angle VMO. Using our trigonometry ratios, we have the opposite side and the adjacent side relative to the angle at M. Inputting this into the calculator, we get approximately 62.7 degrees. In summary, always start by identifying the 2D right-angled triangle that contains the length or angle you need. If you don't have enough information, look for a second triangle that shares a side with the first. 1. Used Pythagoras in 2 steps for cuboid diagonals. 2. Used SOHCAHTOA for the angle between a line and a plane. 3. Solved a pyramid height and face angle by finding internal triangles. You're now ready to tackle 3D geometry problems with confidence. Keep practicing these visualizations.